Hello and welcome to the third in this short series of videos about shortcuts in circuit analysis. This time we're looking at a technique called source transformation, and it can be used to solve circuits like this one. We're asked what the current is flowing through the diode. Now, everything to the left of the diode, you'll notice, is a linear two-terminal network. So we could work out the Thevenin or Norton equivalent circuit for all of these components and then solve a much simpler nonlinear circuit involving the diode. However, this is a reasonably complicated circuit. It's got 5 different sources in it, so even trying to work out the equivalent network by superposition would take us a little bit of time and would be prone to quite a lot of error. The technique of source transformation is a step-by-step technique which, at each stage, does something very simple. It's just that there are quite a large number of stages. Before we start, I need to do a quick revision of some aspects of equivalent networks. As we've seen, there are 2 types of equivalent network, the Thevenin and the Norton. The Thevenin has a voltage source and a series resistor. The Norton, a current source and a parallel resistor. And both can be used to replace any two-terminal linear network. It's very easy to transform from the Thevenin to the Norton equivalent networks because the open circuit voltage, that's just VTH in the Thevenin case, is the Norton current times the resistance. That's IN times RN, and the Norton current, IN, is the short circuit current, and that's just VTH divided by RTH in the Thevenin case. The 2 resistors are the same in both representations. So we can convert from Norton to Thevenin quite easily. Next, we have to note that 2 voltage sources in series add up. So a voltage source V1 in series with a voltage source V2 behaves just like a voltage source V1 plus V2. That's just Kirchhoff's voltage law. And 2 current sources in parallel add up. I1 and I2 behave like a single current source of I1 plus I2. And you get that result by applying Kirchhoff's current law to either the node at A or the node at B, doesn't matter. Finally, we have to note that if you have 2 components like this in series, you can swap the order of them and the rest of the circuit behaves exactly the same. One of the quickest ways to convince yourself that that is true is to consider what the Thevenin equivalent network of each of these sources is. In both cases, the open circuit voltage will be just V1. With no current flowing, there will be no voltage drop across the resistor. And in both cases, the Thevenin equivalent resistance would just be equal to R. Because if you set V1 to 0, i.e. replace it with a wire, you've just got a value of R between A and B in both cases. So these 2 networks would behave exactly the same. Armed with those principles, we are ready to start attacking that circuit using source transformation. And the idea is that we start at one end and we slowly work towards the other end, simplifying the circuit as we go. Stage 1. We have here a voltage source in series with a resistor. That has the form of a Thevenin equivalent network, so we can convert that to a Norton equivalent network by replacing the voltage source with a current source here and moving this resistor from being in series to being in parallel. That gets us to this circuit here. Next, we note we have 2 current sources here in parallel. 2 current sources in parallel behave like a single current source with the sum of the currents. Therefore, we can replace this current source and this current source with this 4.5 milliamp current source. We've got rid of a component. Next. Here we have a resistance and a current source. This has the form of a Norton equivalent network, so we can transform this into a Thevenin equivalent network. The open circuit voltage would be 4.5 times 2, or 9 volts, and the Thevenin equivalent resistance would just be the 2K again, treating this as the Norton equivalent network. I can convert it to this Thevenin equivalent form. Next, I have a 9 volt source in series with a 2 volt source. Well, the 2 volts and the 2K are in series, therefore I can swap the order of them, and that would give me a 9 volt and a 2 volt in series. The 2 volts is backwards in the sense that going from here to here goes up by 9 volts, but going from here to here would go down by 2 volts. So if I moved this 2 volt source over here and combined it with my 9 volt source, I would end up with a 7 volt source. I've reduced the number of components by 1 again. Next, I have a 7 volt source in series with a 2K resistor. That has the form of a Thevenin equivalent network, so I can replace it with its Norton equivalent. In this case, 3.5 milliamps with a parallel 2K resistor. I now have a 2K resistor and a 1K resistor in parallel. They are equivalent to a single 667 ohm resistor, just the parallel combination of a 2K and a 1K. And I've reduced my number of components by 1 again. Next, I have a Norton equivalent form here, which I can convert to a Thevenin equivalent form, and if I did that, I would get a voltage source here and a series resistor. I now have 2 resistors in series. I can combine those 2 resistors in series to a single series resistor, 1K67 in this case. Next, this has the form of a Thevenin equivalent network. So I can convert this to a Norton equivalent form by replacing them with a current source and a parallel resistor. Next, I've now got 2 current sources in parallel. I can replace them with a single current source. I've reduced the number of components by 1 yet again. Next, I've got a current source in parallel with a resistor. That's a Norton equivalent form. So I can convert that to a Thevenin equivalent form, which would have a single voltage source and a single resistor in series. Next, I've got 2 voltage sources in series. I can swap over the order of the resistor and the voltage source, and combine the 2 voltage sources together, and finally end up with this circuit. And this is a much easier circuit to solve. We'd need to do a process of iteration to get an accurate answer, because the diode is a nonlinear component. But that is perhaps a more straightforward method of trying to solve the circuit, certainly by nodal analysis, or by taking all of the left-hand side of the original circuit and converting that to a Thevenin equivalent using superposition. That's the basic idea of source transformation. The point being that if you've got a 2-terminal network here, what you do next depends on what the next component is in the chain of components going towards the other end of the circuit. If the next component is a parallel resistor like this, then you need to get a Norton equivalent circuit in here so you can combine 2 resistors in parallel. Similarly, if the next component was a current source, you would need the Norton equivalent here so you could combine the 2 current sources. On the other hand, if the next component was a resistor in series like this, then you'd want the Thevenin equivalent network here so you could combine the 2 resistors. And if the next component was a voltage like this, then you would want the Thevenin again, because it's easy to combine these two voltages. Occasionally, you might find circuits with a large number of components here, which you've reduced down to a Thevenin or Norton equivalent. And then there is a voltage source on the circuit like this, at which point you go, darn, I've been wasting my time. I didn't need to analyze any of that stuff. I could have just started here and said that the voltage is whatever the voltage source enforces. The voltage here would be just that voltage above here. Similarly, you might have started with a large number of components here and there being a current source. And once again, you've wasted your time analysing any of this circuitry in here. All you have to do is start from this current source and say, I know that the current from all of this stuff is just the value of this current source. I can carry on from here. You'll note that this only works for certain types of circuits, sometimes called ladder circuits, which have this general form. I've drawn them as resistors, but these components could be voltage sources or current sources, but they'd all be in this type of arrangement. But this turns out to be a very common topology of circuits. So source transformation is a useful technique to have in your arsenal. A quick summary of things so far then. Remember that nodal analysis will get you to the answer eventually, but it is very much a last resort. If you can use superposition or equivalent circuits or source transformation to save yourself some time, then do. Okay, that's all for this one. There's only one little video left in this topic, and that's about the maximum power theorem.